This is Mr. Sitta. I'm going to go over the quiz I posted, and this is real quick. We're going to look for patterns, orbital patterns. So you're always going to start with the periodic table, and you want to remember the patterns that you can find on the periodic table. The regions are S block filling, P block, D block, and F block. Smart people don't forget. S block starts at energy level 1, runs through 7, technically goes all the way to infinity. P block starts at level 2, energy level 2. Okay. D block comes after you fill a 4s, but then it starts at the third level. F block fills after the 6s, and all you have to do is follow the atomic numbers. This would be 55, and it goes to 56. Goes all the way to 70, and then you go back and fill the 5D. So if I did any configuration, my order is really right here. 1s followed by 2s, followed by 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, down to 4f, back down to 5d, 6p, 7s, 5f, back to 6d, and 7p. If you follow that configuration, every orbital notation you does have the same order. It's just where you end. And you end at that element, and you're just filling in the electrons where they go. So I'll give you this on the test, and this is where I would always start. I'd start with the letter designation for your orbital types. It's S, P, D, F. Smart people don't forget. Fill it in the periodic table. S, P, D, F. I've done this before. Quantum number designation. Okay. S's are always designated as 0. P's are 1. D's are 2. And F's are 3. Okay. There's 4 quantum numbers. The first quantum number was energy level, N equals. On the periodic table, it just corresponds to your period. 1, 2, 3, 4, 5, 6, 7. If I was to look at the S's, it corresponds to, if I drew an atom in 3 direct dimensions, Z, Y, and X axis. That corresponds to what we saw as the Bohr model shells. Energy level 1, 2, 3, 4, and I'll just take it to 5. It'd go all the way to 6 and 7. Okay. And that's what you see as level 1, S, 2s, 3s, 4s, 5s, 6s, and 7s. So these outer ones correspond to your shells in a Bohr model. The P's are a different shape. There's 3 shapes for a P. So if I was to look at, they don't start till level 2. So again, I'll put an N on this side. 1, 2, 3, 4, 5, 6, 7. P start right here, 2, then 3, 4, 5, 6, and 7. That'd be a P. Okay. What do they look like? Again, you get 1 P in this direction, in the Z direction, so I'll call it a PZ. You get a PY in this direction, and you get a PY in this direction, PZ X. Okay, so when you look at those 3 P's, if I separate them out, you have one lobe in this direction, you have one lobe in this direction, and you have one lobe in the x-axis direction. Now, when we do orbital notation, we're just going to make circles for those. And our quantum designation will be m sub l. So for a p, your l is a 1. Well, m sub l is plus or minus l. So it's just a way of designating that these are different. Plus 1, 0, minus 1. So an electron can go here, here, and here. Okay. The energy levels. What energy level do they begin with? N. Well, S's start at level 1. And again, this is a nice block to write off right at the beginning of a test, because then you can look at test questions and answer them very easy. There's an empty space right here, because there is no such thing as a 1p. P's start at level 2. There are empty spaces right here. Okay, there's nothing here and there's nothing here. Why? Because D's don't start until now. It looks like you're at level 4, but what they actually do is they actually fill inner orbitals. So D's start here. I'm just going to put them in. And they start at level 3, 4, 5, 6. Technically, they exist for infinity. Okay, and I have a rough time showing the shape of a D, but basically a D is filling. You see that empty area where you have a hole? The D fills that region. It's where, as the atom gets bigger, you can put electrons there. They actually will fit there. You don't see them at low levels, because at low levels you're very small and there's a lot of electrical repulsion. As the atom grows, you get more regions, you get more orbitals. Technically, your number of orbitals is, if you take energy level squared, that's your number of orbitals. Okay, so if I say level 1, 1 squared is 1, there's only one orbital at level 1, and that is the s. 2 squared at level 2 is 4. There's your 1s. And you have 3, 1, 2, 3 p orbitals. That's a total of 4. If you go to level 3, you get your 1s, your 3 p's, that's 4. And then the d's run 5 across. Well, each one represents an electron being added. And an orbital holds 2 electrons. So if you take your 10 divided by 2, there's 5 d's. So 2 plus 3 plus 5 gives you 9. So square that, that's your number of orbitals. Level 4, 4 squared is 16. 1s, 3 p's, 5 d's, that's a total of 9. Your f's hold 14 electrons. Well, that's divided by 2, so it's 7 f orbitals is what you get. And 7 plus 9 is 16. So that's a mathematical function. The number of orbitals is n squared. Okay, go back to your d's. We said they start at level 3. If you follow your pattern 1, 2, 3, you know your s should start at level 4. And where do s begin? When you're filling your 6s and then you go into the f, it's actually filling an inner f, which is at level 4. It'll start at 4f1. Then you'll have 5f1 right underneath it. Halfway full would be 4f7, which you'd have 5f7 right under that. And then when you're full, you'll have 4f14. Okay, so you just run 1 through 7 as you add electrons. Okay. Number of electrons. The alkalis all have 1 electron, which they end up losing. That's why they become a +1. The alkali earths all have s2. 3s2, 4s2, 5s2, 6s2, 7s2. I'm not going to fill everyone in this table. As one example, if I start my P's, I start off with 2p1, 2p2, 2p3, 2p4, 2p5, all the way to 2p6. Except for helium, which will be 1s2. Helium sometimes will fit it right in here. It is a noble gas. It does have a full shell, it just doesn't have any P's. If I go all the way down, I get 3p6, 4p6, 5p6, 7p6, and 6p6, and 7p6. If I went down 3, each one would be p3 in a family. So 2p1 all the way down. Okay, so that's across, and that's down. You'd start with 3d1, 3d2, 3, 4, this would be 5, 3d6, 3d7, 3d8, 3d9, and you'd end with 3d10. Outer layer 4d10, 5d10, and 6d10. And you would start off with 4d1, level 5d1, level 6d1. So that's just generally what your periodic table looks like. Your L designations, if you have an L equals, if it's an S, it's a 0. If it's a P, it's a 1. If it's a D, it's a 2. And if it's an F, it's a 3. Well, this is a way to designate your third quantum number, which is which orientation does it enter. So they use M sub L, which I like to call orientation of orbital. Your quantum number, they'll say, oh, magnetic quantum number, but that wouldn't mean much to you. So if I say S is equal to 0, M sub L is equal to plus or minus whatever L is. So 0, and I get a 0. If I get a 1, I get 3 solutions. I get plus 1, 0, negative 1. That corresponds to 3 orbitals. Mathematically, if I do a D, plus or minus 2, I get plus 2, plus 1, 0, minus 1, minus 2. That corresponds to 1, 2, 3, 4, 5 orbitals. Okay, so there's 5 Ds times 2, they hold 10. Fs, you get plus or minus every L is your M sub L. So you get plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. I'm making up a pretty good sheet that shows you the pictures of the orbitals. We can answer this question. How many electrons are able to exist in any given orbital? 2. How many Fs are at any given energy level? Well, this is a total of 7 Fs. So each one, when we represent orbital notation, we represent them as circles. Each one gets a circle. 1, 2, 3, 1 for 0, 4, 5, 6, 7. So there's 7 Fs. Okay. How many P's? 1, 2, 3. How many S's? Just 1. It's designated 0. D, 1, 2, 3, 4, 5. S is really 0 because it's a perfect sphere. It has no angular momentum. These numbers really are representing like angular momentum of the electron in the different axis directions. Okay, so that's your number of orbitals. Okay, let's go to the back. Write out the full configuration for phosphorus now. I'm going to use a periodic. I always do these off the periodic table. Here's phosphorus, which has a total of 15 electrons. It's number 15. So phosphorus has 15 electrons. We want to show where those electrons go. Now, I want you to do an electron configuration, which is your first two quantum numbers, and orbital notation, which is your second quantum two numbers. The orbital notations really, they never change. So I can just say, you start off with single for the S, you start off with another circle for the 2s, you'll get 3 circles for a P all the time. Then you follow another S, and then you get 3 more circles for a P. Okay, then you would get, if you keep going, another circle for the S, and then your D's come. 1, 2, 3, 4, 5, and then you get 1, 2, 3 for the P. So this configuration is always 1S, 2S, 2P, 3S, 3P, 4S, 3D. That's right here on the periodic table. So here's where your electrons go. Working my way up to phosphorus, they start with level 1 and an S2. So I get 1s2. Now I'm at helium. That would be the configuration of helium. 2 more, 1, 2 would be in level 2, s orbital, and 2 fit there. That's 4 electrons. Then I go into level 2p. How many fit there? 1, 2, 3, 4, 5, 6. You're just filling electrons. That's a total of 10. And from here to here, these are your inner core electrons. They are represented by neon. So if I stopped right there, that would be the configuration of neon. Now comes the outside electrons. The outer electrons are in level 3. These are called your valence electrons. 3s2, 1, 2, and then here's where you stop. It's just a matter of knowing where to stop. 3p, 1, 2, 3, and I'm done. 3p3. I never got up to here, so I don't really need to use it. Now, you have quantum filling rules. First of all, 2 electrons are going to fit in every one of these circles. Okay? 1 electron is going to spin in one direction, and the other will spin in the opposite. That's because of Pauli exclusion principle. No 2 electrons can have the same 4 quantum numbers. So you can never have 2 electrons in an orbital spinning in the same direction. And that's why you can only have 2, because if you put a third in, 2 of them are going to have the same spin. Your first rule to remember is Hund's off-balls rule. That is, you start filling your orbitals with the lowest available energy, the ground state. So this would be an excited state up here. I have 2 in the S, so I go 1, 2. Okay. Now comes Hund's rule. It's called multiple multiplicity, because Hund's rule only comes into play when you have 3 equal orbitals. The rule says this: you have to fill one at a time, and their spin has to be parallel. So it's up, 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 and then down, down, down. And that's 6. That's 2, that's 2. 2 in the S, 1 up, 1 down. And it doesn't matter really whether I go up or down, as long as they're spinning parallel. So you don't put 2 in the same orbital, because electrons repel each other. So if you look at your orbitals, they're not going to go in the same orbital because they push away from each other. They're going to go into an empty orbital region. And that will look like phosphorus. These are called your valence electrons. These are the outer shell electrons that are lost, gained, or shared in a bond. Right out of noble gas configuration, you take your last occurring noble gas. So if I was looking at phosphorus, your last noble gas is always up 1 level all the way to the right, neon. Just like counting backwards, you're at 15, the last one was number 10, neon. So what you do is you say, this is a full configuration. Now it's just shorthand. Phosphorus equals everything that neon had. And in the end run, we really just want to know about these valence electrons. 3s2, and 3p3. Now, how does this affect the behavior of phosphorus? You have an opening for 3, you can potentially fit 3 electrons. Now, if I do a Lewis dot diagram of phosphorus, these 2 electrons are the 2 that are in the s. These are showing my outer valence, and then I get 1, 2, 3. I have 2 possibilities. If phosphorus bonds with something, it is willing to share 1, 2, 3. Share 3 electrons, so form 3 bonds. Or it could gain electrons. If it just gains electrons from a metal, then it would have a full octet, a full 8, and there's a negative 3 charge that you know phosphorus always gets. Okay. Carbon, going back one, would bond to 4 things. Oxygen only bonds to 2 things. Halogens only bond to 1 thing because they're P5. Oxygen's P4, so it only has 2 electrons to bond with. So that's where you get the idea that phosphorus can get a negative 3 charge. It's going to pick up 3. Alright, we'll go through our filling rules real fast, and then I'm done this. Off-ball principle says B. Electrons fill the lowest available energy orbitals first. Down here is an example for each rule. If I see a number 15, there's no electron in there. It's jumped up to here, so that's an excited state. So this is an example of the off-ball principle being violated. Now, later on when I show you 3 exceptions, the 3 exceptions actually, in their lowest state, they violate the off-ball principle. But because they're actually in the excited state, they're actually in the lower energy level because of their characteristics, which we'll talk. I have that on video. Okay. Hund's rule of multiple multiplicity. Hund's rule comes in when you have 3 multiple orbitals. Well, there's 1 and there's 2. These are both violations of Hund's. This one should be spinning up, not down, so parallel. And this one, the electrons should go in them one at a time, so that's both of these are Hund's rules. And then Pauli exclusion is a very easy rule. Here's Hund's rule on here, multiple choice. Electrons fill energy orbitals one at a time with parallel spin. So that's C. And then no 2 electrons may possess the same 4 quantum numbers. That's Pauli exclusion. There's only one way you see Pauli. You can't have 2 electrons in the same orbital with the same spin. Then all their quantum numbers would be the same. And it also tells you that if you already have 2, you can't put a third in. So these are both Pauli exclusion, and then there's your 2 in the same orbital. That would be Pauli exclusion principle. And then finally, number 17, there's no 2 with the same spin. Everything's at its lowest state. These 3 are in properly, so this one is no violation. Okay. What element is shown above in it? It ends in a 3p2. So it's very easy for me to just go to the periodic table and say, okay, here's 3p.